We are going to start talking about logarithms. The logarithm of y with base b is denoted by log with base b of y and is defined as log of base by equals x if and only if b to the x equals y. This right here is something you may want to pause and write down. Notice it says x is the power you must raise 10 to get y. Okay, so you have your number equals, when you see log, it's the power you must raise the base to get the number that's next to the base. So if I want to rewrite this equation in exponential form, you take the base, the exponent is on the other side of the equal sign, so it would be 2 to the third equals the 8. Base to the other side of the equation equals the number that's left. So for this one, I would write 5 squared equals 25. And as you'll notice, that is also true. 5 squared does equal 25. Next one, 7 to the negative 2 equals 1 over 49. And again, if I were to put this 7 to the negative 2, bring it to the bottom of the fraction, so it would be 1 over 7 squared. That would be 1/49. And then the last one would be 6 to the first equals 6. Now we're going to rewrite the equation in logarithmic form. So first I'm going to write log. Now the 2 is the base of the log, just like it's the base of the power. The other side of the equal sign is going to be the exponent, and the 32 is the number that goes after the base. So log of base 2, 32 equals 5. Next one, log. The base is 5. On the other side of the equal sign is the exponent, and the 1 is after the base. Log with base 1/2. On the other side of the equal sign is the negative 1 exponent, and then we have 2. 1/2 to the negative 1 equals 2. And for the last one, log of base 4. On the other side of the equal sign is the exponent, and then 16 is left. 4 squared equals the 16. Crazy dog. Special log values. If you have a logarithm of 1, for example, log of base b1 equals 0. That's because b to the 0 always equals 1. So anytime you have a log with a 1 right here, you're going to have 0 on the other side of the equal sign, because anything to the 0 is 1. And then log of base b, when you have log of base b and then this is the same number next to the base, it's always going to be 1. When you have log of base b, anytime you take that to the first, you're going to get that number back. Evaluate without a calculator. Just assume that this equals x, okay? And x is what I'm trying to solve for. Remember, the base of the log has an exponent that's on the other side of the equal sign. So what you're really thinking is 2 to what power is going to give you the 4. So log of 4 with base 2 is going to be what? So 2 to what number equals 4? The exponent would be 2, because 2 squared is 4. 2 to what power would give us 32? That exponent would be 5. 7 to what power would give us 1? And that's one of those things that we just talked about. Log of 1 with any base is going to be 0, because anything to the 0 power is 1. Now we have 1/3 to what power would give us 27? Now, in order for this 3 to get back up to the top to give us a 27 over 1, you're going to have a negative exponent. Okay, but you still think 3 to what power would give us 27? Well, 3 to the third is 27, and it's going to have to be negative to get that back up to the top of a fraction. Next one, 8 to what power would give us 2? Okay, now notice that I'm getting smaller, so I'm going to have to take a root of 8 to get this 2. What root of 8 can I get 2? Well, another way to think of it is 2 to what power gives us 8? It'd be 2 to the third. So it would be the cubed root of 8 would give us 2. Okay? The cubed root of 8 would give us 2. And then how do we write this with an exponent? Remember, the index goes to the bottom, and this is 8 to the first. So the exponent on the 8 would be a 1/3. And then for the last one, 8 to what would give us 64? That would just be 2. 8 squared is 64. Crazy dog. Common logs. A log with base 10 is denoted with just a log, L-O-G, and that's what we call a common log. Okay, because it always is going to have a base 10. So if you see log and it doesn't have any other base, the base is 10. Okay, and then a natural log is denoted ln. Okay, anytime you see ln, it's not going to have a base on it. That base is always e. Okay, so anytime you see log without a base, the base is 10. Anytime you see ln without a base, that base is e. Now what you're going to do is just go ahead and use your calculator to evaluate. On your graphing calculator, you can just hit log and then type in the number, or ln and then type in the number. If you have a scientific that doesn't show your typing as you go, you would have to type in, for this first one, log 6. You would type in the 6 first and then log, and you'd get an answer of 0.778. Notice we're rounding our answers to the thousandth place, which is 3 decimal places. If you type in log of 0.4, you're going to get negative 0.398. Log 3.72 is 0.571. Natural log of 8 is going to be 2.079. Natural log of 0.23 is negative 1.470. Natural log of 6.12 is 1.812. Okay? Notice that when you take the log of a smaller decimal, one that is less than 1, we're getting a negative answer. Okay? If it's a number less than 1 that you're taking a log of, whether it's a common log or a natural log, you're going to get a negative answer for those. Finding inverses. We're not actually going to find inverses at this point, but I just want to show you something by definition. Here's the point I want to make. G of f of x equals log base b of b to the x, and that equals x. Basically what this right here is saying, okay, the proof of this composition function, since it's x, basically what that tells us is when we have a log of base b with the same here, those actually cancel each other out, leaving us with just the x. Okay? And when we do this composition function, when you have the same base b to the log of the same base b, those cancel out and you are left with just x. And that actually should have an equal sign there. Okay? In essence, those things undo each other. To show some examples of that, when I have 7 to the log base 7 of x, these two basically undo each other, leaving us with an answer of x. Same thing with this next one. Since these two bases are the same, they will undo each other, leaving us with just the exponent, which is x. Okay? Same thing with this one. The 13 and the log base 13 undo each other. we're left with 5x. This one's a little trickier. Notice the base is 2. I can get this 8 to have a base of 2 if I change it to 2 to the third. Okay, so I changed 8 to 2 to the third, but then that's still to the x. I can rewrite that as log with base 2 of 2 to the 3x. Okay, I can put these together because that's my property of exponents. I can multiply those. Now I have the same bases. Log base 2 of 2 leaves me with the exponent of just 3x. Now remember, when you have just a log without a base, that's like having log base 10. So I'm going to change 10,000 to 10 cubed. And then since that has an exponent of x, I'm going to combine those. So I've got 3x as my exponent. Now since this is a log with base 10, a common log, that will cancel out with a base of 10 here, leaving me with 3x. Now with this last one, I need these bases to be the same. I've got log base 3. I want the base of this power to have a base of 3, so I'm going to change 27 to 3 cubed, but then that's still to the 2x. Now using my properties of exponents, I'm going to rewrite 3 cubed to the 2x as 3 to the 6x. Now these two will undo each other, leaving me with just 6x. And that concludes section 7.4, the first part.